Hey everyone, today we're going to tackle one of those classic programming hurdles, arrays versus linked lists. Look, if you've ever felt a little fuzzy on this topic, you are absolutely in the right place. We're going to break it all down and show you why getting this concept is a total game changer for your coding. So let's just dive right in.
All right, so let's start with a really common problem. You need to keep a list of something, but you have no idea how big it's going to get. You're going to be adding stuff, removing stuff. It's just constantly in flux. A standard array can be a real pain to work with here. And this is the exact scenario that linked lists were built for.
Okay, here's the main idea you gotta hold on to. Think of an array like a rigid box, kind of like a pill organizer, with a fixed number of spots. A linked list, on the other hand, is way more like a flexible chain. You can add a new link or take one away anywhere you want. It's super dynamic. So just keep this box versus chain idea in your head, because it is the key to understanding everything else we're about to cover.
So how do we actually build one of these flexible chains? Well, it all comes down to one simple but really powerful building block. Let's take a closer look at what that is. This little block is called a node, and its design is just beautifully simple. It really only does two things. First, it holds your data, a number, a word, whatever you need to store. And second, it holds a pointer, which is really just an address that tells you where to find the next node in the chain. And that's it. It's just some data and a signpost pointing to what's next.
And here's how you actually string those nodes together. Every list has to start somewhere, right? We call that first node the head. From there, you just play connect the dots, following the next pointer from one node to the next. Now, when you finally get to the end of the chain, the very last node's pointer doesn't point to anything. It points to null, which is just a universal signal for stop. The list ends here. Okay, so we've got our chain built. Awesome. Now what? Let's get into how we can actually use it. This is where we get into the nitty-gritty of how these things work.
So the most basic thing you can do is called traversal. It's a fancy word for a simple idea, just walking through the list. You start at the head, and you follow each next pointer until you hit the end. And you got to remember this, because traversal is what I like to call the hidden cost of linked lists. Why? Because to do almost anything, find an item, add something new, even just count how many items there are, you have to walk the list first.
You can really see this hidden cost pop up when we talk about adding new items. If you want to add a new node right at the front, at the head of the list, it is lightning fast. We call this O1, or constant time. It means it takes the same amount of time whether the list has 5 nodes or 5 million. But if you want to insert a node anywhere else, you've got to traverse the list to find the right spot. And the time that takes grows along with the list. We call that ON, or linear time. Now, here is a huge, huge warning. When you're inserting a new node, the order you do things in is absolutely critical. If you mess up the pointers and overwrite a link too early, you can literally break your chain in half and lose the rest of your list forever. It's a classic rookie mistake, so just be really careful with your pointers.
Deleting a node works with pretty similar logic. You can't just, pluck a node out from the middle. The trick is to find the node that comes right before the one you want to delete. Once you find it, you just change its next pointer to jump or skip over the node you're removing. That connects the chain back together and poof, the unwanted node is effectively gone.
So the basic linked list is really powerful, but it's kind of a one-way street, right? You can only move forward. So let's check out a couple of cool upgrades that make these chains even smarter and way more flexible.
The list we've been talking about is a singly linked list. It's a one-way street. But then there's the doubly linked list, and you can think of that as a two-way street. Each node now has 2 pointers, the next pointer we know, and now a prev pointer for previous. This one simple change lets you move through the list forwards and backwards, which, as you can imagine, opens up a ton of new possibilities.
So why would you ever need this? Well, think about your web browser's back and forward buttons. That is a perfect real-world example of a doubly linked list in action. There's also another cool variation called a circular list, where the very last node points back to the head, creating a loop. This is great for stuff that needs to cycle endlessly, like taking turns in a game or managing tasks in a round-robin schedule.
All right, it is time. Time for the main event. We've seen what linked lists can do. Now let's put them head-to-head against arrays and see how they really stack up.
This table pretty much says it all. Arrays store everything together in one big chunk of memory. That's why jumping to a specific spot using its index is super fast, O of 1 fast. Linked lists, though, they have to start at the head and walk the whole chain, which makes getting to an index much slower. That's O of n. But the tables completely turn when you want to add or remove something from the front. For a linked list, it's a super fast O of 1 pointer change. For an array, you might have to shuffle every single element over, and that is a painfully slow O of n operation.
So all of this leads us to a really simple rule of thumb. If your main priority is getting to elements quickly just by knowing their position, you're going to want an array. But if you know you'll be doing a lot of adding and removing, especially at the beginning or end of the list, a linked list is definitely going to be your best friend.
So let's wrap this all up with the single most important idea I want you to walk away with.
I really love this quote. Efficiency isn't doing more, it's choosing what makes the common case easy. It's never about which data structure is just better in some abstract way. It's always about which one is better for the specific job that you're trying to do. It's about picking the right tool for the task at hand.
And I'll leave you with a final thought to chew on. Think about a social media feed, where new posts are constantly being added to the top as you scroll. Based on everything we just talked about, which tool would you reach for first? An array or a linked list? Think about it. Thanks for tuning in, and I'll catch you on the next one.